Hello, people. We are going to do the notes for that's funny, the ratio test. It is the last test that we'll talk about. There are some others that we can use to test whether a series converges or not, but they are not included on the AP test. There's a couple other little exceptions that we'll sprinkle in as we talk about stuff, but this is basically it. And the ratio test is, besides geometric series test, ratio test is used all the time. So it's definitely the most popular test that they will ask you about after geometric series test. So the ratio test is really weird. And it basically says, let's say we have some series, and we're going to take that series. We're going to be comparing the n+1th term and the nth term. This is weird, but we're going to be taking the limit, and it'll make sense as I do a couple problems, or at least you'll understand as I do a couple problems. We're going to look at the limit as n goes to infinity of the series, plugging in n+1 for all the n's, divided by the series itself. And when we do that, we're going to get some number. We're going to call that number L. If that number, or I should say, if the absolute value of that number is less than 1, then the series is going to converge. So you can see with these tests, there are all these little well, if this happens, then this, and if this is this, whoops, that is less than 1. If this is this, then that. It's a lot to remember, and when we finish this up, I will kind of go through each one, and maybe I can write it all out. So it's like, okay, here's the direct comparison test, here's the nth term test, here's the ratio test, here's geometric series, here's the integral test. So you kind of have them all in one spot. So the ratio test says if we take the limit of the n+1th term over the nth term, we're going to get some number. If that number is less than 1, or the absolute value is less than 1, which really just means if L is between 1 and -1, then the series will converge. If that limit that we get is bigger than 1, the series will diverge. It's not like we're undecided. We're going to get a converging or a divergence out of this test with one exception, and that is if L equals 1, then the test is inconclusive. So that's why this is used so much, because it's really can be very helpful. If the limit is less than 1, we converge, greater than 1, diverge. That's like a definitive answer. The only time we don't get a definitive answer is if that limit equals 1, and then we say that that test is inconclusive. So, okay, so what does that mean? So let's take an example. Oh shoot, I don't have a ton of space here. Whatever. Okay, so let's say this example. Does the series e to the -n converge or diverge? Now this is actually geometric, but let's just look at it through the lens of the ratio test to take a somewhat easier series and look at it with ratio test, because later on we'll look at it in we'll look at more complicated ones. So let's look at an easier one to start. So first of all, realize this is the same thing as 1 over e to the n. It's a lot easier to think about this as a fraction as opposed to a negative exponent. So the first thing I always will do is I always will stop and think about the nth term test. I will make sure that the limit as n goes to infinity of 1 over e to the n is 0. And it is. Bottom grows faster than the top. The top's a constant. So that means I can keep going. That is just the nth term test. It's how I start. It's how I try to start every problem, just to make sure that it's worth continuing, that we don't have a divergent series right from the beginning. If this happened to have an n factorial on the top, I would stop, because that limit would not be 0. That limit would be infinity, so I would stop. But okay, so I've done that. I'm just going to get rid of this to give myself space. So I'm going to apply the ratio test. If I knew what I was doing and if I wasn't teaching this lesson, I would do this with geometric series. I would make sure my r is less than 1, or between -1 and 1. But let's just say I'm going to use the ratio test just for giggles. So the ratio test says I'm going to look at the limit as n approaches infinity, and I'm going to make a big fraction. On the top of that fraction, I'm going to replace all of my terms with n plus 1. And on the bottom, I'm going to have my series with the n's. So it's going to look like this. I'm going to take the limit of this, but I'm going to replace all of my n's with n plus 1s for the top of this fraction. And on the bottom, I'm going to have the series itself, 1 over e to the n. And I'm going to figure out what this equals. This is going to become a numeric answer for me. And I'm going to look at that numeric answer and decide if it means my series converges or diverges. Oops, based on the number of that answer. So for most of these, I'm going to have to flip and multiply. So this is going to equal the limit as n goes to infinity. I'm going to take the bottom fraction, flip it, and make multiplication. So I have 1 over e to the n plus 1 times e to the n. Okay, let's do a little bit more algebra and get this together a little bit better. So this is the limit as n approaches infinity of e to the n over e to the n plus 1. This is not a plus 1 that I ignore. This is a plus 1 that I actually do consider. And I'm going to reduce this. So there's going to be a lot of reducing of fractions to try to get myself a numeric answer out of this. So how can I reduce e to the n over e to the n plus 1? I'm going to use exponent rules. So it might be a while since you've learned exponent rules. I think someone asked in class the other day. Remember the other day in class we had the square root of n over n squared, and that resulted with 1 over n to the 3/2. If you felt confused by that, we need to brush up on your exponent rules. That to reduce that, all I'm really doing is I'm subtracting exponents. I'm thinking about the square root of n as n to the 1/2, and I'm subtracting because I have the same base. This becomes n to the 1/2 minus 2, which is n to the negative 3/2, which is how I got that. So hopefully that made sense in class the other day. You didn't feel too confused because the same thing's going to happen right now. So I'm going to reduce this by subtracting the exponents because I have the same base. So this is going to equal, sorry about being all over the place, e to the n minus n plus 1. I'm going to subtract the exponents, the top one minus the bottom one. So this reduces to e to the negative first. This distributes. So n minus n is 0, and then minus the 1 is negative 1. So this reduces to the limit as n goes to infinity of 1 over e, of 1 over e, but there's no, that's it. There is no n here. So this is just going to be 1 over e. This limit equals 1 over e. I get a numeric answer. And now I just have to take that numeric answer and decide, did that numeric answer, which we're calling L, is that L between 1 and negative 1, or is the absolute value of it bigger than 1, or does it equal 1? Well, 1 over e is like 1 over 2.7, so that is between 1 and negative 1. So therefore, my series will converge. Sorry about being so sloppy. So we could say 1 over e, the absolute value of 1 over e is less than 1. So by the ratio test, the series converges. It's as simple as that, although when I look at this computer screen in front of me, it doesn't look like I did something that was simple. But it isn't that bad. It's very algebraic. The only tough part really comes in the reducing and the remembering what to do with exponents. But it's not going to be too bad. I mean, spoiler, it gets a little bit more difficult with tomorrow's video. With today's video, it's going to be not too bad. So let's see. Okay, let's just get rid of everything and try another example. So let's try one that the geometric series test wouldn't work for. By the way, the geometric series test would have worked for the last one. When I have 1 over e to the n, this is just a geometric series. When n is 1, I have 1 over e squared, 1 over e to the third, and so on. So my multiplier is 1 over e. Well, that's less than 1, so this would have converged by the geometric series test. I wouldn't have even needed the ratio test, but I wanted to show you one that was somewhat simple. So let's look at another one that I would not be able to use geometric series. Let's say, does this series converge or diverge? N to the 10th over 10 to the n. That's interesting. I'm going to go 0, but I don't really know why. It's just because of what my example says, but it doesn't really matter. So the first thing I still want to consider is I want to consider the nth term test. I want to make sure it's worth continuing. So if I look at the limit of the whole series itself, nothing's changed. Will I get 0? So in other words, does the bottom grow faster than the top? Yes. This top is like a polynomial, n to the 10th. And there's no other terms, but still that's how it grows. 10 to the n is exponential. That's way bigger. So yes, this is going to become 0. So it's worth continuing. I know I keep saying it, but that's the only reason why the nth term test is helpful, is just to determine if it's worth continuing. So it is. So this is not geometric. Notice if I start plugging in numbers, if I just wanted to like prove to myself it's not, when I plug in 0, I get 0. But then when I plug in 1, I would get 1 over 10. When I plug in 2, I'm going to get 2 to the 10th over 100. Plug in 3, I'm going to get 3 to the 10th over 1,000. So I do have a common multiplier for the denominators, but not the tops. There's no common multiplier to get to make that happen. In fact, starting at 0 would also screw me up. But anyway, there's no common multiplier for those tops. So not geometric. So other than being geometric, I could think about direct comparison test, but neither n to the 10th nor 10 to the n or something are things that I'm super familiar with. Although I guess, no, I couldn't even compare it to geometric series or anything. So I'm kind of stuck. So let's try the ratio test. So again, ratio test says take the limit as n approaches infinity, make a big fraction. On the top of that fraction, we're going to plug n plus 1 in for all of these n's. And on the bottom, we're going to have this exact same thing. So the top is going to become n plus 1 to the 10th over 10 to the n plus 1. And the bottom is going to be the exact same series I see here. Next step is going to be, let's get this bottom fraction flipped and use multiplication. So I'm going to have the limit as n approaches infinity of n plus 1 to the 10th over 10 to the n plus 1 times 10 to the n over n to the 10th. Flip that bottom fraction and multiply. Now, to find this limit, I want to, my strategy is I want to stack common things over common things. What I mean by that is, right now it looks a little bit crazy with all this all over the place. 10 to the n and 10 to the n plus 1, they're going to reduce well with each other. I want to look at them over each other. And n plus 1 to the 10th over n to the 10th would also compare well with each other. So I'm going to rewrite this. And I'm going to put 10 to the n over 10 to the n plus 1. And I'm going to put n plus 1 to the 10th over n to the 10th. I'm totally allowed to do that. This is all just multiplication. So these are all multiplied. These are all multiplied. It doesn't matter what order I put them in on the top and bottom. So I'm just going to stack things a little bit differently so I can do some comparing. So I really want to see what happens with these. What happens with these? So with the 10 to the n and the 10 to the n plus 1, let's reduce that. And I end up with, look at my powers. I have an n and an n plus 1 I'm going to subtract. So I end up with 10 to the negative first. I hope that makes sense. I'm taking 10 and I'm going n minus n plus 1. So I've left 10 to the negative first. And this doesn't really reduce. This on top is a big polynomial that would have to get FOILed out. I'm not going to do that foiling. That would be ridiculous. But what I do have, on the bottom, I know my biggest term is n to the 10th. And on the top, I know I'm going to have an n to the 10th plus a ton of other stuff. But all I really care about is I'm going to really just care about comparing those two lead terms. So not to confuse you, you're like, yeah, too late for that. Oops. I'll leave this as is, and then I'll talk about it in a second. Okay, so now I'm ready to take the limit now. I'm ready to see what happens. So when I do limits, I have these two parts that are multiplied. I'm going to do them one at a time. I'm going to say, what does this part of the limit go to, and what does this part of the limit go to? And of course, I ran out of room on the bottom. Let me give myself some room up here. I'm going to rewrite so it's a little bit neater. So what I'm looking at here is the limit as n goes to infinity of 1/10 times n plus 1 to the 10th over n to the 10th. The reason I'm writing it up here is to give myself a little room underneath it, just so you can see how the way I write things down, the way I think about it. I need to really evaluate this limit as two separate parts that are multiplied together. Well, what does this part go to? 1/10 as n goes to infinity becomes 1/10. I don't have any n's in that part, so that's going to go to 1/10. This is going to go to 1 because the top and the bottom have the same degree. The top of this is a 10 or a power of 10 plus a bunch of other terms, but who cares? They're like inconsequential to us, and the power that is predominant on the bottom is also the 10th. So I'm really comparing an n to the 10th to an n to the 10th. If there were coefficients, if I had like a 2 here and a 3 here, this would go to 2/3. I'm really saying, okay, as n goes to infinity, I have n to the 10th over n to the 10th, so I'm taking the ratio of the coefficients. They have the same growth rate as n goes to infinity, so the ratio of the coefficients is 1. So this limit is going to 1/10 times 1, so this limit is 1/10. So let's evaluate that. Let's look at the rules. Oh, oops, the rules are already erased, sorry. But the rule said whatever our limit is, as long as that limit is between 1 and -1, as long as the absolute value is less than 1, then my series converges. Yeah, so that is the ratio test. Let me see if I can find another decent example. You're going to have to work through some problems, and I will do a video for the problems. There's one more I want to show you, and that is, what do we do with a factorial? So how do we apply ratio test to factorials? So let's go through that. So let's say, hold on, the lights in here turned out. Let me stand up. Okay, let's look at, I'm going to try to write more smally, tinier, smaller, whatever. Oh shoot, where did I put that problem? Oh, here we go. How do we handle factorials? So let's say we have the series n plus 3 factorial over 3 factorial n factorial 3 to the n. Oops, this must be a 1. Not there. Okay, what? Spoiler alert, whenever I have factorials, unless it's a really simple problem, I'm going to be using the ratio test. So I'm going to use the ratio test for this, but it's going to look really crazy. So let's see what it looks like. I'm going to take the limit. Maybe you want to pause the video and set the limit up yourself to make sure you have it right. So I'm going to be making a really big fraction out of this. Now, with the ratio test, you know how I'm making a big fraction, right? And on the top of it, I'm putting n plus 1s. On the bottom, I'm just putting the series itself. But then you notice the next step is always take the bottom fraction and flip it and make it multiplication. Why not just skip right to that? I'm going to skip right to that so I don't have to write it another time. Instead of writing it as a fraction, I'm going to write the top with the n plus 1s. I'm going to flip and multiply all at once so I don't have to write this twice. So I'm going to be looking at the limit of n plus 1 plus 3 factorial over 3 factorial n plus 1 factorial 3 to the n plus 1. So that's the top of my fraction. So again, on the bottom, what I would get is I would get n plus 3 factorial over 3 factorial n factorial 3 to the n. And then my next step would be flip and multiply. So instead of writing that, I'm going to just, well, I mean, obviously I wrote it, but in the future, I'm going to just flip it right away. So instead of writing it at all like this, I'm going to write multiply instead of divide, and I'm going to flip the fraction all at once. So 3 factorial, n factorial, 3 to the n, over n plus 3 factorial. So I think it's just easier to have it written like that instead of all the writing and the fractions and the flipping. Okay, so the next step is, let's write same things over same things. So I can do the comparing and the reducing. So I'm going to write, first of all, do you see 3 factorial and 3 factorial just going to cancel with each other? Great, let's just let them be done. Here I'm going to have n plus 4 factorial. I'm going to have n factorial, and I'm going to have a 3 to the n. On the bottom, I'm going to have, in fact, whoops, I'm going to make little fractions out of this. Times fraction. On the bottom, I'm going to have an n plus 1 factorial. I'm going to put that under here. No, I'm not actually. Lies. I'm going to put that under the n factorial. Oh, shoot, that's the bell. I'm going to put this under here and this under here. We're going to have to pause this video and come back. Let's see if I can get that to actually work. I'm going to pause it right now. Hi, guys. I'm going to try to finish recording this, but a study hall is coming in. So let's see how it goes. So how do I reduce factorials? That's going to be my big question. Let me just try to finish this before they come in. So I need to reduce this, I need to reduce this, and I need to reduce this. So for my factorials, here's the way to think about it. Let's think about these factorials expanded. So this top factorial is n plus 4. What would the next term be? If I'm doing factorials, the next term is 1 less than it. So it's n plus 3, and then n plus 2, and so on. Well, on the bottom, I have n plus 3, and then the next term would be 1 less than it. The next term would be 1 less than it, and so on. Well, watch what happens. Everything here will cancel with everything here, and all I'm going to have left is n plus 4. That's going to happen here as well. Watch what happens. So if I take this part, how do I reduce these factorials? Well, on the top, I would have an n, and then I'd have an n minus 1, and then I have an n minus 2, and so forth. On the bottom, I have an n plus 1, and then I'm going to be multiplying by 1 less than that, n. And then n minus 1, and then n minus 2. Well, watch what happens. All of this cancels with all of that, and all I'm left with is this. To reduce this part, I subtract my exponents. So I'm going to have 3 to the negative first. So what that means is, as I reduce this limit, I'm going to have the limit as n approaches infinity of n plus 4 over n plus 1 times a third. That's all that's left on the top. That's all that's left on the bottom, and then a 1/3. The limit of this guy is just 1. Degrees are the same. Ratio of the coefficients is 1. The limit of this is just 1/3. The limit is going to equal 1/3. Is the absolute value of that less than 1? Yes. So this is going to converge by the ratio test. That is really, really rushed. So hopefully you can slow it down and make sense of it. And I'll make sure that we go through another example, but that's how you reduce factorials.